Okay, it's loading. Okay, so I think that we are live on YouTube. So, okay, it's loading. All right, so, okay, so I think we can start. Welcome everybody to the first QPK talk of this new season. So this is the first QPK talk of 2022. So today we have the honor to receive Professor Lea Santos. For those who don't know, she's Brazilian, so this is quite amazing. Actually, I have to apologize. I sent her some emails in English while she was replying me in Portuguese, but this is because I was also sending other emails in English, so I got a little bit confused. But it's a great pleasure to receive Professor Lea Santos, and so that's it for the next, let's say, 40 minutes, but not restrictly. The screen is all yours. So thank you very much.
Okay, so I'd like to thank Pedro Enrique and Luca Celeri for this invitation, you all for showing up. A great pleasure to be here with you. So here you have pictures of people who have been involved in the results I'll present to you, and I'll come back to their names later, okay? But the goal of this discussion is to talk about how long it takes for quantum systems. They're isolated, or let's say quasi-isolated, and which have many interacting particles to finally reach an equilibrium. The idea is we know what equilibration and even what thermalization is in these systems. What is not so clear yet is how long it takes to reach this point, okay? But to tell you about equilibration, let me tell you first what we mean by equilibration. So the idea is we pick an observable, let it evolve, and I can write these evolved states in terms of the components of this initial state. So these are the C alphas that you're seeing here. And in terms of these phases, these E alpha, E betas are the eigenvalues of the Hamiltonian that is evolving the system. And you also see these O beta alpha, which are the off-diagonal elements. So you see, the way I wrote this equation is I separated the term where alpha and beta are different, which is the one that controls the evolution, and when alpha and beta are equal. So this is time independent. What we have to keep in our minds is we are dealing with many body quantum systems. So we'll have many, many phases here, and the system doesn't have the geners, so it has few degenerates, so lots of phases. The systems are perturbed very far from equilibrium, so these components here are very small. And the systems are complex, the eigenstates are complex. What I mean by that is these eigenstates here are close to like random vectors. So these off-diagonal elements are much smaller than the diagonal elements. All that to tell you that this term, after some time, will just give us fluctuations around the second term, which is the infinite time average. And so after some time, this term is averaged out. So we reach this point where we have tiny fluctuations around the infinite time average. That's what we call equilibration. So we know these fluctuations are small, we study them, we know that they decrease exponentially with system size. We reach this point, that's what we are calling equilibrium. A second step of this question is then to compare this infinite time average with a thermodynamic average, like a microcanonical ensemble. If they coincide, that's what we call thermalization, it's one step more. And a condition for thermalization is that we have quantum chaos. I'll come back to this later, but just keep in mind properties as in random matrices, okay? Anyway, all of these questions, equilibration, thermalization, spread of information, how fast the system evolves, they are not just theoretical questions. There is a lot of experimental interest, and you know about these experiments. No? Coherent evolution has been studied for a long time in NMR. There are people in Rio who do great experiments in NMR. And now the big sensation, these experiments with optical lattices, ion traps, because they are highly controllable and well isolated. all of these setups that I'm mentioning here to you can be used to simulate spin-half models. And that's the kind of systems that we'll be talking about. Okay, so let me come back to our question. We want to know how long it takes for isolated many-body quantum systems perturbed far from equilibrium to finally reach a new kind of equilibrium. This time should be bounded by what we call Heisenberg time. Now, the Heisenberg time is the longest possible time scale of the system. The Heisenberg time is the inverse of the mean level spacing. But what is the problem with that? This is a many-body quantum system, so the Hilbert space grows exponentially with system size. The number of levels grows exponentially with system size. So the inverse of this mean level space in this Heisenberg time grows exponentially with the system size. So if I have to wait this long to talk about equilibration, then does it make sense to talk about equilibration? Okay, so the question is there, what is it that we are going to call equilibrium? And then many items. How does this time depend on the system size? Does it increase? Does it decrease with the system size? How does it depend on the model? If it's interacting, non-interacting, long range, do we have a chaos or not, in the sense that I'll tell you later? How does it depend on the initial state? These many-body quantum systems that have two body couplings or few body couplings, if you look at their density of states, is Gaussian. No? So histogram of eigenvalues, Gaussian. What does that mean? That we have many, many levels in the middle and fewer levels at the edges. So if I pick an initial state with energy here in the middle, it should evolve much faster than if I pick an initial state that has energy at the edges. So there should be a dependence on the initial state as well. And finally, how does this time depend on the quantity that we are studying? Yeah. If we find that different quantities equilibrate at different time scales, then again, what is equilibration? Do we have to wait for all of them to equilibrate, or we talk about equilibration? Yes.
Sorry to interrupt you. Are we talking about the only boundary Hamiltonians, boundary from above? I mean,
yeah. Yes. That's why I have both. Yes, I'm talking about okay. Models. Yeah, I'm not talking about like DK model and unbounded systems. No.
Okay. Thank you.
These ones where we have, and that's why I have lowest values and largest values, eigenvalues. Okay, so look, I decided to start this presentation with some results from an experiment, because I know Lucas is interested in NMR experiments, and I thought other people in Goiás also. And it kind of relates with quantum information. So this beginning will be short, is a description of an experiment, and then later I go for some theoretical results, and I think will be partial because we won't have much time. But let's see. I'm going to start with this one because I thought you might like. Yeah. So this is an NMR experiment that was done with David Corrett and Mohammed Niknam, where we proposed and we measured a new entropy, which we call correlation Rényi entropy. And we did that for the central spin model. So the purpose of this work was really to measure experimentally a new entropy. But you will see that the results fall within this big question that I'm asking you, which is, what is equilibration time? That was not the main purpose of this work. This work is about this entropy. And what did we find out? See, this blue line here is this correlation Rényi entropy, and the brown entanglement entropy. And what we see is that the correlation Rényi entropy keeps growing for much longer than the entanglement entropy. The entanglement entropy already saturated while our entropy is growing. So that discussion that I had with you before, does the equilibration time depend on the quantity we are studying? Okay. But anyway, so let's start discussing a little bit about entropies. You know very well the entanglement entropy. I'm sure many of you are interested in quantum information. So you trace out part of the system and you focus on the reduced density matrix. And then compute the von Neumann entropy for this reduced density matrix. That's what we call entanglement entropy. And, well, looks like a sophisticated entropy, but it was measured experimentally, and you may know about these experiments. No? First, it was done with superconducting qubits, just 3, qubits, but that was already something. No? Then there was the experiment with cold atoms, the group by Greiner, where they had 6 sites. It was not exactly the entanglement entropy, but it was they deal with the squared of the reduced density matrix, also an entropy. No? And this same entropy was measured now more recently with ion traps. And here they had a reasonably large size, now already 20 ions. So a lot of the experimental interest in the entanglement entropy, but there are other entropies as well. No? So let's think about this idea. Suppose we start with a spin configuration like that, an initial state where we have spins. I'm thinking about spins half again. So some are pointing up, some are pointing down in a certain direction, let's say Z direction. As the state evolves, it's going to, I don't know, from site 5 here, this spin is going to flip to 4, then from 4 to 3. So this state is going to spread out in this many-body Hilbert space. What we can do is then look at the probability to find our evolved state in this configuration or in that configuration. So this is what I'm calling the CK squares. See, there's the probabilities. And I can collect all of these probabilities and measure any entropy I want. I can use it to compute the Shannon entropy, no, which is the first order Rényi entropy, or I could use them for the second order Rényi entropy, or any entropy, any order that we may want. So you see what this entropy is measuring is the spread. It's not necessarily concerned with growth of entanglement. No? So it's an interesting entropy, for example, in studies of localization. But it hasn't been measured experimentally yet. Our entropy is close in spirit to this one. We are concerned with this spread, not necessarily entanglement. Okay? Our entropy is very close to this idea of the out-of-time order correlated. Now, what is the out-of-time order correlated? The square of the commutator between 2 operators. At time 0, this commutator may be 0 or something very small, but as time passes, this commutator grows. So supposedly, an exponential growth indicates chaos. So there is a lot of discussion. So this exponential rate is now called quantum Lyapunov exponent. Just as a detail, and if you want, I can discuss more this with you. It's true. Now, this has been studied and confirmed for systems where you have the quantum and the classical limit. But this exponential growth also shows up for regular systems when you are at a critical point. Okay, but this is a detail parenthesis. Let me come back to this out-of-time order correlated. So suppose the operator that is evolving, let's assume this W is a spin operator on a single site. So I'm marking it here in red. And so I'm thinking here about a spin chain. As time grows, we can see what is going to happen by expanding this exponential. So we get these nested commutators. What they will be telling us is that, well, this operator is changing, this operator is spreading in this chain. And the OTOC, this out-of-time order correlator, will measure this growth. So this is very similar to our entropy. What we are going to do, here is the density matrix for the whole system. I'll tell you now about the system, but just let me start giving you the idea, okay? And this is the expression for its evolution. The density matrix for us initially is just one Pauli matrix associated with one spin. But let's look at the evolution. The evolution creates those commutators. At very short times, just this first commutator is important. As time grows, well, the double commutator will become important, and the triple, and so on. So what the commutators will create is, instead of a Pauli matrix for just one spin, I now have a Pauli matrix for one more spin. That's what this double commutator gives me. Oh, this first commutator. The double commutators give me 2 more. So what this term is telling us is that now these 2 spins are correlated. This next term is now telling me that I have 3 spins that are correlated. Our entropy will measure that. How this number of this term grows. So our entropy measures the growth of multi-spin correlations. Okay, so this is the idea. Now I go more into details. So what is the system? The system is a molecule, the name is there. Here at the center, we have a spin half, and this spin half is directly coupled, is interacting with 15 other spin half which are around. So the interaction is this, the ZZ term. No? So sigma Pauli matrices, no? So the ZZ term, and this is the interaction strength, dipolar interaction. So this interaction strength decreases cubically with the distance from the central spin and the surrounding ones. The surrounding spin, these 15 surrounding spins, they are also interacting through this other Hamiltonian, is also dipolar, but also with the flip-flop. Now what we did in this experiment is take advantage of NMR techniques, not the idea of the spin echo, to get rid of this term, to average out the effect of this term, to average out the effect of this. There's an echo. There's an echo.
Yes. Yes.
Okay. Under control. Okay.
Oh my God.
Under control.
Oh my God.
Continue. Okay. Okay. There is this echo. Is it for everybody also?
Yes, it's happening for me, but I don't know how to solve this problem.
Pedro, I think that Thales is with the microphone on. You
Okay.
can mute everybody, except Lea, of course.
The speaker. I'll say, look, it's gone. It's gone. So let's continue. Yeah. So what I told you that we average out this, the interactions around the surrounding spins. Now we kill them. We kill their effect. So you see, we end up with something very, very simple, just this Hamiltonian. So the experiment is done at room temperature, very good isolation from external bath, and we have in total 16 spins. So what is the idea? The central spin, so CS here is the central spin, it's initially polarized in the X direction, so the sigma X. The surrounding spins, they are completely unpolarized, so we have this fully mixed state, okay? But we have this interaction between the central spin and the surrounding one. So what is going to happen is the information which is initially in the central spin is going to spread out to the surrounding spins. And how can we measure this loss of information? What people often do in NMR is to measure what they call the free induction decay, which is this trace of this initial state to the Pauli matrix X in the central spin and the evolved density matrix for the central spin. So this at time 0 is 1. And then as time goes, it decays. No? So the free induction decay decays. The Hamiltonian is very simple, so you can write all this in a closed form. This is one quantity. The other quantity that we could measure is like the entanglement entropy computed for that central spin. The experiment only has access to the central spin. No, you only get the signal, you only get the information from the central spin. So we can look at the entanglement entropy for that reduced density matrix of the central spin. And again, the results are very similar. You see these Fs here, they are directly related with the free induction decay. So if I look at this one or that one, we get similar results, similar information. What do we have here? What I'm showing to you in this panel is just a numerical results, because then it gives me the chance to explain to you how the experiment is done. Yeah? So each line here corresponds to one set of that interaction strength, these omega J's that you see in the Hamiltonian. This set depends on the orientation of the molecule, okay? But in NMR, the NMR signal doesn't come from one set at a time. It comes from a huge ensemble of molecules. So what we really have is the average, which I indicated with this black line. Yeah. So free induction decay or entanglement entropy, you see similar behavior after 200 microseconds. It has saturated. Let's now compare with our entropy. Let me come back to that slide where we talked about the evolution of this density matrix for the whole system, yeah? And we expanded the exponential, and we have those commutators. Now you know what the initial state is, right? This initial state is the sigma x just for the central spin surrounding fully mixed state, and you know the Hamiltonian ZZ. Okay, so if I look at this commutator of x with z gives me a y, but that's not what I'm interested in. What we are interested in is that together with it, we got a z from one of the surrounding spins. Double commutators, we got two z's, and triple more and more. So the thing goes growing. So what I do is I'm going to collect each one of these terms here. So here's the one that I have just one spin. Here's all the terms where we have one spin for the surrounding, all the terms with two spins for the surrounding, and so on. The experiment is going to measure, that's what is special about this experiment, each one of these amplitudes, not really in the z direction. I'm not giving you all the annoying things about the details of the experiment. It does measure each one of these amplitudes in the x direction, but the point is it does. So we look at these weights, and then we use these weights to compute our entropy. So it's a simple idea, but what is special here is what the experiment can do. Now, how do we compare this entropy with the entanglement entropy? So let's come back to the entanglement entropy. Remember, we had to trace out the surrounding spins. Tracing out the surrounding spins means tracing out these Pauli matrices, which are z, +1 and -1. So when we do that trace, we kill all of these terms. The only one that survives in the entanglement entropy is this one, which is fine. The C0 is telling us about the loss of information. But our entropy has more. It's not telling us just about the loss of information, it's where this information is going, how it's getting shared with the surrounding spins, how these multi-spin correlations are being built. Yeah. So these symbols here are results really from the experiment, and lines are numerical results. Okay, so the symbols here, the one that is decaying first is that C0. As C0 decays, then C1 starts growing, and then C2, and then C3. So you see the build-up of each one of those terms. And then we collect all of these C's to compute an entropy, and then it can be any entropy. First order, any entropy, second order, any order that you may want. Yeah. So symbols are, as I told you, the experiment, and what do we see as we compare the correlation Rényi entropy with the entanglement entropy? You see the entanglement entropy died around 200, while 200 here, we are still growing. And so we are still building up these correlations. Then I want to pause here with you to say something that was bothering us, because the only reason why we build up correlations is because what was in the central one is getting out. So how come here it looks like things are dead and we're still growing here? Yeah? So after this, then we said, wait a second, let's have a look at this line. Yeah? So we zoom in a lot, and the scale is ridiculous, no? But 0.99 to 1. But you see, it's still growing. So here, it's still growing. So we are still losing information from the central one. Of course, it wouldn't occur to you to look at that if you didn't know about the correlations, and no experiment would be able to detect that we are
Sorry,
still...
Lea.
Who is...
Can I ask a question?
Yeah.
So this entanglement entropy is between the central spin and the rest, is that?
Yes, yes.
And if you look at like two spins with the rest, like trying to look my multipartite, maybe they are still increasing?
Yes, and even here it's still increasing. And there are tons of things to be done still here. What I'm showing to you is what the experiment can do, right? Because the experiment can only look at the central spin. You can play with many things, and I can tell you more. We also want to take into account the interactions among the surrounding spins, which we killed for this experiment. So there are many, many things to do. I'm just showing to you what we have so far for the experiment, showing that that discussion that I was having with you in the beginning. Well, depends on the quantity. I have saturation times at different time scales. Yeah.
So maybe one interesting is that the correlation entropy, like measuring the single spin, you can still see these many particle correlations, and without but with the entanglement entropy, you cannot see it. No?
Yeah, no, but because the correlation Rényi entropy, the experiment only has access to the center spin. But in NMR, what they do is it's a sequence of rotations and so on that I'm avoiding telling you because it would be tedious, I think. But they place all the information about those correlations. So they place all the information about these terms into the central spin via phases. Yeah, so they have to do many Fourier transfer and so on. So they have information about each one of these in the phases that goes into the central spin. So even though they only measure the central spin, they are really measuring each one of those terms. So it's really special technique. Yeah, while the entanglement entropy is really concerned only with that loss of information. Yeah, but I agree with you. There are tons of things to be done, and if anyone wants to help me, let me know. Yeah, but anyway, so here we are with two quantities that saturate at different times. The experiment ends around 550 microseconds. The next slide is numerics. We just wanted to see, okay, when does it finally saturate? And we see saturation here at 2000 microseconds. This is numerics only, which is 1 order of magnitude longer than what we are seeing for the entanglement entropy. Okay? So I repeat, the goal of this experiment was showing we can measure this growth of correlations very similar to the out of time order correlated, this spread. But you see that the results bring me to this broad question that I'm asking you, what is this equilibration time? And we see it depends also on the quantity. Okay, so this is the first part of the talk. I told you it would be short. I'm going to go to the second part, which is longer and theoretical. If you want to ask anything else about this one, let me know.
I do, actually.
Yeah.
I'm just, curious because you went through a very long time in the experiment, 500 microseconds. Should we expect some sort of returning of the information to the central spin due to the finite size of the Hilbert space?
Yeah, well, yes, we talked a lot about this. We are measuring these correlations, right, Lucas? Yeah, but in these correlations, you have things that are there in the central spin as well. We are not thinking about backup of information. We have many discussions about this growth. Is this environment Markovian or non-Markovian, this kind of things. Yeah, it's another interesting question, things to study. Yeah, but we didn't focus on that. Yeah.
Oh, okay, thank you.
Yeah, okay, so this is one point, an experiment showing to us two different quantities, giving us different saturation times. What I'm going to do now is talk about theory. And here I'm going to base the discussion on this result that was done with Thalia, is a postdoc working with me, but it comes from many, many studies with Jonathan Torres and Mauro Schulas, who were postdocs working with me, and discussions with senior people. But let's summarize the story. Okay, so what is it that I'm going to show to you is that depending on the quantity that we select, here is a survival probability, we see that the time to saturate grows exponentially with system size. So this is what I was telling you before, Heisenberg time, which is crazy. Or depending on the other quantities that we select, we see still growing with system size, but polynomially. So let me try to give you an idea of these results. And to illustrate these results, I'm going to pick one spin half model in one dimension. So sigma the Pauli matrices. Let me just tell you briefly what this Hamiltonian is. Forget about the ZZ term for the moment. Let's look just at the X, X, Y, Y. So what this term does is when it acts on a state like this, where the spin is pointing up in the z direction, the other one is pointing down, it flips them. And so we get now down up. So this term moves my spin up, moves my excitation from one side to the other. Now, what we also have in this Hamiltonian is this other term, which is a term of on-site disorder. So what this term is telling us is that on each side, we have a different Zeeman splitting, okay? So suppose I have an excitation here. This term wants to move this excitation to the neighboring sides. But because of this other term, we have this mismatch in energy. So this gets hard. And in one dimension, no matter how small this mismatch is, no matter how small this on-site disorder is, the system is localized. So this is the idea of Anderson localization. Now, when we bring into this story the ZZ term, this is the easy interaction. When we bring this to the story, then this interplay between the interaction and the on-site disorder delocalizes the system. The system becomes chaotic in the sense that I'll tell you. So then the question, which is now called many-body localization, is whether can we still get a localization if we increase this disorder strength, okay? And this is something for people in Brazil, this discussion on many-body localization we did in 2004. I'm sure many of you remember Carlos Escobar. He's now retired, but I was a work with him, and Gustavo Rigolin, who is a professor in São Carlos. Yeah, so this is 2004. The pioneer work about many-body localization is Basco, Alainer, Altschuler, 2006. Yeah. Okay, so I told you that once we add the interaction to this story, the system becomes chaotic. I'll tell you now what we mean by that. Let me tell you one more thing that you may also find interesting. What I realized in 2004 is that even if I add a single defect, a single site with Zeeman splitting different from the others, that also makes the system chaotic. So this model now has many studies for transport behavior, for people who are interested in transport behavior. It has some interesting features. Anyway, what is chaos? Okay. And to tell you about chaos, let me tell you a little bit about random matrices first. Random matrices are matrices filled with random numbers. And I already see here 835. Pedro, should I continue or you want me to?
Yes, please. No problem. It's no problem. There's no problem for me. I think we can continue.
Okay, so this is, I think, nice for the students. Random matrices are matrices completely filled with random numbers. The only constraint is that they should satisfy the symmetries of the systems that we are studying. So our systems here, the matrices are real and symmetric. So if I want to compare random matrices with them, I'm going to use matrices that are real and symmetric. Okay, they were used by Wigner back in the 50s to describe statistically the spectra of heavy nuclei. Well, the idea is heavy nuclei is such a complicated system. Well, instead of going for all the details of these interactions, let me fill the matrix with random numbers. Okay, so you diagonalize these matrices and they have interesting properties. For example, if you look at the spacings of the eigenvalues, now, so if you look at the spaces between the neighboring levels, make a histogram. For random matrices, you get a curve that looks like this red one. So it tells us that there is no degeneracy, there is no spacing zero. The levels repel each other, they are sort of correlated. So the levels repel each other. That's what you see for random matrix. Well, this is data from a real nucleus, and you see it matches very well. So it's fascinating. That's such a simple idea that works so well, and was then extended to other complex systems, molecules, atoms, and so on. Where is the story of chaos coming from? Later, in studies of billiards back in the 80s. What people realized studying billiards, now billiards in a classical limit, when the billiard was chaotic, and chaotic in the sense of positively autonomic exponent, extreme sensitivity to initial conditions, mixing, then when they would study the billiard in the quantum domain, the levels would follow the Wigner-Dyson distribution. On the other hand, if the classical system was regular, then in the quantum domain, you would get a Poisson. So the Poisson tells us that the levels now are uncorrelated. Yes, they can cross. Okay? So this established a relationship between level statistics and chaos in the classical limit. Okay? So what we call quantum chaos is just that, signatures that you found down there in the quantum domain that tells you whether the system in the classical limit is chaotic or not. Now, this is well established for systems with few degrees of freedom, like billiards or kick rotor, decay model, not yet for the systems that we are interested in, which are systems with many degrees of freedom. Okay, what we are going to do in this talk is, if I see Wigner-Dyson, I'll say, the system is chaotic. If I see Poisson, I'm the system is not chaotic, without checking the classical limit. Okay, and this is an oversimplification. There are other things in between this Poisson and Wigner-Dyson, and also I don't have this classical limit. So if it disturbs you, and it should, okay, this term quantum chaos, you can substitute it by just properties similar to what we have in random matrices, okay? So coming back to this model, when a disorder strength is small, so this H is the disorder strength, is small with respect to what? With respect to this coupling strength, then we have Wigner-Dyson distribution. As we increase this disorder strength, so it gets larger than the coupling, this gets more and more deformed, eventually we get to the Poisson. And as we go from one side to the other, what happens is the eigenstates here in the chaotic region are extended, delocalized in space. As we move to this region, they become localized in space, okay? What does it mean, localized, delocalized? Let's have a look at eigenstates. We are dealing here with eigenstates that are huge, many body quantum systems. So we have many, many coefficients here. We are writing this eigenstate in a certain basis. How can I know how many basis vectors contribute to this state? What is the participation of these basis vectors? So we use, for example, the participation ratio, which is 1 over these coefficients to the 4th. What this quantity tells us, if we have few states participating, so we'll have few C's that are different from 0, the participation ratio is small. If we have many participating, if the state is very much delocalized, we have many tiny C's, then the participation ratio is large. In random matrices, all of the eigenstates are just random vectors. So they are all completely delocalized. The participation ratio is proportional to the dimension of the Hilbert space. So what I'm showing in this plot is the participation ratio for each one of the eigenstates, and you see flat here, proportional to the dimension of the Hilbert space. In realistic systems, the story is different. Even there in the chaotic domain, we do get states that are very much delocalized, but in the middle of the spectrum. At the edges, they are not, okay? Anyway, all that to say, in this model, as we move from the chaotic region, if I look at the participation ratio, we see that here in the chaotic region, the participation ratio is proportional to the dimension of the Hilbert space. As we increase the disorder, then the participation ratio decays, indicating that the states are becoming localized. So this is the analysis that we did with Carlos Escobar. And this you will see if you're dealing with finite systems. The big question now is whether this transition, let me just finish. So whether this transition still exists in the thermodynamic limit. What was the question?
Hi, it's Thiago again. So you are plotting the participation ratio of the eigenstates when you decompose it in the local spin base. Is that correct?
Right, because we are studying, and this is what I put here to indicate what is the base, because we are studying localization in real space. This quantity depends on the basis that you select. So how are you going to choose the basis? According to the question that you're interested. If you want to study localization in space, you pick this basis. But if you wanted to study localization in some other basis, you would pick the other basis. Anyway, so there are many things to tell you here, so maybe I can meet with you another time to tell you about these transitions and so on. For this talk, I'm only going to base it on the chaotic region some very general results. And Pedro, again, should I try to summarize, or I have many slides, but should I try to summarize?
Yeah, I think so. But don't worry.
I'm not going to go
Okay.
for the details. People who may want the details, I can talk to you in private, yeah? But so focusing only on this chaotic region, I'm going to skip many slides. We did a comparison of the evolution for the disordered spin model, but this is general. This result serves to other chaotic systems. We compare this evolution with the evolution of the full random matrices. This is very unphysical, but it's a nice comparison, just as Vigna did the comparison between heavy nuclei and random matrices, okay? And we studied this quantity, the survival probability. There are many steps to explain to you each one of the terms of these final expressions, which are this is really analytical expression. This is a semi-analytical expression that describes the whole evolution of the survival probability. With these analytical and semi-analytical expressions, we can get the time scales, including the time here for the saturation. And from this expression, so it comes analytically, the result that we find is, skip all that, the result that we find is, well, this saturation time grows and grows with the dimension of the Hilbert space. So what is this saturation time that you're seeing here? Is the Heisenberg time, which is something to worry about. If it's taking that long, can we talk about equilibration or not? There is a feature in the dynamics, which is this dip here. This dip that you see below the saturation point is what is known as correlation hole. It only shows up in systems where the eigenvalues are correlated. This dip is, you may have read about this dip. It's called correlation hole in quantum chaos. But in high energy physics, now people call this the ramp. And this name ramp has propagated in condensed matter physics. People also calling ramp because you reach this minimum and you go up on the ramp. Anyway, this feature here, you may say, oh, maybe this feature will disappear in time, so maybe I should think about the saturation being earlier. Well, this feature for this quantity does not disappear. It's always there, okay? And we can show this numerically and analytically. And then you may say, then is the survival probability is a problematic quantity. Look at another quantity. We looked at this one, which is the spin autocorrelation function. You study the magnetization at a later time, compare with the initial magnetization. This is similar to the density imbalance measured in cold atoms. And there again, the correlation hole is there saying the saturation happens after this correlation hole. So super long time. There is a nice thing of seeing this correlation hole for this quantity, because it could be a way for people who do cold atoms experiments or ion traps to detect chaos, to detect level statistics from the dynamics, because these people don't have direct access to the spectrum. So this is a nice feature, but there you are, this super long time. What we notice, and this was the work with Thalia, however, is if I study this hole, it disappears for this quantity at long times. This plot is telling us that it's disappearing for large system sizes. It is there for short system size, but it goes on shrinking for large size. And the other quantities, remember the entropy that I told you that was measuring the spread in the Hilbert space? So this quantity is that entropy. We don't see the hole there. Well, it's one of those features. It is there. If you zoom in a lot, you will see that it's there. So if I would talk about saturation, I would talk about it after the hole, but again, it's minimum. And it disappears again as I increase the system size. And now it shrinks. It's already, you almost don't see it, no? And it shrinks exponentially with the system size. All that just to tell you that we said, okay, so maybe for these other quantities, it justifies neglecting this feature of the dynamics, this correlation hole, and talk about saturation before that feature. So this is what we are marking with this cross. And then we see, well, it's still growing with system size, but now at least it's growing polynomially with the system size. So I skipped many details here, but the message is that we talked about the dependence on this equilibration time on the quantity and on the dynamical features that we will or not take into account. Yeah, but thank you for your attention. Sorry for being too long.
Yeah, thank you very much, Lea. Do we have questions? Lucas?
I have many questions. I mean,
Yeah,
Yeah,
too. I mean, yeah.
but,
Lea,
but also we can always talk together in private if you want, Tiago and Lucas. But go on.
of course. Well, first of
Yes.
all, many thanks for the talk. Do we have anyone in the audience that doesn't speak English? Yeah, the Sheng is here. Okay, Lea, I was looking at your equations about the participation ratio and the survival probability in these things, and this looks like a bunch with the Loschmidt echo.
Oh yeah, it is.
And the reason why I'm interested in these things is because Pedro, which is here, and Anderson also here, and also the Sheng, they're interested in the dynamical quantum phase transition, which is characterized by the Loschmidt echo. The survival probability, but psi 0 is the ground state manifold.
No, the real echo. You go and come back. No, people in NMR. Sorry, Lucas. People in NMR cannot call this Loschmidt echo. This is not Loschmidt echo. But go on. Sorry.
And is there any relation that you know about between thermalization times and actually equilibration in general, and systems that have dynamical quantum phase transition or not? Or even what happens if I have a usual equilibrium phase transition in the middle of the dynamics? What happens with these results?
Well,
with this deep and everything else?
I don't know because I didn't study, but let's see. First, the Loschmidt echo is something that I thought about including it. I just stick to the survival probability because we could get analytical results. Yeah. For the Loschmidt echo, it gets more complicated, but we can do things numerically as we did for the other quantities. And it would be a nice thing to see if we could or not find this correlation hole in the Loschmidt echo as well. I doubt it. I think it would be closer to that other quantity, something like that. Yeah, but it would be nice to see. And then again, checking this time for the Loschmidt echo. Now, once you think about any special features, quantum phase transitions, even there is something called excited state quantum phase transitions. If we reach those critical points, then you find many different results. We see survival probability almost freezing. Then there are many different features to analyze. We can discuss and we can try to do things numerically. I don't know.
Yeah, I'm very interested in studying these dynamical quantum phase transition to see, I mean, what happens with information spreading all over the Hilbert space, but when we go through these critical regions.
Yeah, and then because then I think it's nice if you're going to study dynamical quantities. Well, you can look at entanglement entropy, but you can look at this kind of spread that I was talking about also. No? So there are different quantities that you can try to explore. You can look at survival probability, and for the survival probability, I didn't tell you, but we know a lot, like all the details. We know about each step of the evolution, we know where it's coming from, because everything about the survival probability is so simple, because the survival probability is just Fourier transform of the energy distribution of the initial state. So I look at the energy distribution of the initial state, I know everything about it. So that's something that we can look at this energy distribution if you are close to a transition or not, and see how this changes. So then you will know first what happens to the survival probability, and then you can look at other quantities. I see Pedro take.
That's interesting. Yeah.
But Pedro, we can talk, and I explain to you exactly how to do this. It's simple. Yeah.
Yes, actually, I never noticed that the survival probability is the
Fourier
Fourier.
transform of this
Yeah.
energy distribution. It's very
Yeah,
simple. And
This is
then
quite
if you have a Gaussian shape, the behavior will be Gaussian decay. If you have a Lorentzian, the decay will be exponential. So you get lots of information. Also, since you're all interested in quantum information, the survival probability is the quantity that is used to see the fastest possible decay that you can have via the energy time uncertainty principle. The fastest possible decay is a cosine square, coming just from the energy time uncertainty relationship. And that's also another nice thing. Is there any energy distribution here that would give you this limit in the quantum speed limit?
That's nice. That's nice.
And I have some results. If you want, I can show to you about this quantum speed limit. And there are many interesting papers, Seth Lloyd and other people.
Yeah, of course. I'm quite interested too. Thiago. Oh, sorry, Lucas. Do you have more questions?
Well, I have, but I mean, let Thiago say.
Yeah, actually, I have a very specific question here. So, have you has anyone looked at what happened with this survival probability of the fidelity when the energy distribution is bimodal? You don't have one Gaussian, but like you have two Gaussians separated.
Yes, yeah. Well, very nice that you do. You have any energy distribution like that?
Because,
do you have?
No, I mean, no. Actually, I'm not really. So maybe I didn't really make the questions correctly. I mean, I'm not thinking about the energy distribution. I'm thinking about preparing an initial state such that your coefficients are going to have like this. So it's going to be like a microscopic superposition.
Okay. So this is exactly what I was telling them about the quantum speed limit. We reach the quantum speed limit if I manage to have two peaks. Yeah. So we knew that, because if I have two peaks, think about just two lines. So if I had just the initial state was just a superposition of two eigenstates. So what is this decay? Cosine. This you can show. That's what we learn in course in quantum mechanics. The behavior is a cosine square. This is the quantum speed limit. Now we knew that. So the bimodal kind of distribution for the initial state will give you the quantum. You reach the bound for the quantum speed limit. Now, we did that by hand, forcing it, but it's not realistic. Okay, remember that model that I told you with the single effect. So why is not realistic? My initial state is an initial state from this part of the Hamiltonian. So that's not something that an experimentalist could prepare. And then I let it evolve with this Hamiltonian. So I put this impurity really big. So I create two Gaussians. Yeah. So it's not realistic, but I wanted to reach that quantum speed limit, so I put it by hand. But if we could have an initial state that has this bimodal distribution, but is physical, for a model that is physical, that would be super nice for this question. Okay. I see things in the chat. Okay, so it's Rafael and Lucas. Yeah.
Any more questions?
So, I mean, also, I was thinking about this Rényi entropy you defined. So, because I know people also have defined like channel entropy. You pick some state, you decompose it in a base, and then you use the coefficients. You calculate the entropy of the coefficients, no?
Right.
So
exactly.
I was thinking that you could start with an initial spin configuration in the spin basis, and then as it's going to evolve in the Hamiltonian, you're going to start to have a superposition of how many of these guys, no? And then you could, so in the beginning you just have one coefficient, and then the local basis you have a lot of coefficients. So Is this, you could use this, some kind of a channel Rényi entropy of this coefficient. Is this similar or relate to what you're doing there? I mean, it's...
No, this we did. We have many studies of this, theoretical. Yeah, so this is exactly what you said, that the probability to BD or probability. Then we have theoretical results trying to get some analytical results for that. Yeah, but I didn't see any experimentalists computing this quantity, which I think is the most obvious one. I would go for this one before going to entanglement entropy, because entanglement entropy, we do tomography, all these complicated things. But yeah, but it's not what our entropy did. The entropy with the experimentalists is measuring the spread, but it's counting on those multi-spin correlations. But theoretically, yes, this is what a quantity that I was suggesting now to Pedro and Lucas also. And it's nice because you see, here we are not concerned about growth of entanglement, it's spread. But at the end, it shows behaviors very similar to the entanglement entropy. Remember this story about entanglement entropy? Once you go into localized phase, or when you're reaching the localized phase, it starts growing linearly, and then it becomes lower, a logarithm behavior. Well, same thing for this entropy, is linearly, and then it becomes logarithm. And then we have more. The slope of this logarithm behavior, when we make a log plot, we can compare that slope with the spread of the initial state. So there are more things that we can do, I think, than directly with entanglement entropy. It's easier, I think.
Lea, two questions actually. What happens when we choose a different order for the Rényi entropy? I mean, because you just pick up the second order. So what happens?
No, this is a very good point. And this goes for dynamics. Also, this is very nice, Lucas. For dynamics, and also just, I can use these quantities just to measure the eigenstate, right? I pick the eigenstate, I can use these quantities just as the participation ratio to see. Remember that, let me go back there. Let me start from this, and then I tell you about dynamics.
I'm asking because I'm very interested in this thing. I recently published a paper relating the different orders of Rényi entropy, also Thales entropy, with the quantum speed limit.
Yes, okay. So this is nice because, and if you ever have a model where you can also study the classical limit, it's nice. Why? Higher orders, what they will do is the tiny values are just, since it's, if you look at a higher moment, the components that are very small will practically disappear. So if you go high moments, you're going to enhance the ones that participate the most. If you go low moments, and you can play here, you don't need to go 2, 4, you can play with a 0.5, 0.3, which is what is called generalized participation ratios. And then you're going to enhance this spreading. So playing with these moments is very nice. Also in that energy distribution, which is something that, remember this energy distribution I was telling Pedro, if you look at different moments, you're going to enhance different features of that energy distribution, so you can get more details. Yeah? And so this is what is happening at the level of the eigenstates, and also for dynamics. You'll be enhancing bigger or smaller participating elements. So that's a nice thing to play with. What was your result about checking the different Rényi entropies?
We bounded the change for closed systems. We bounded the change in Rényi and Thales entropy and related this with quantum speed limit. Let me check here. But while I check this here, my second question is, I mean, is there any relation between the results that you get from spreading of information with the some sort of bound, like Libby-Robinson bound? Is there any connection between these quantities and Libby-Robinson bound?
That I never thought about.
Because it should be, you know.
There should be. What we did look at, and this I think would be an interesting point, because, okay, this initial growth of this quantity, remember I told you this linear growth, what we try to mark is that slope, we connect it with the width of that energy distribution of the initial state. So that, so remember the energy distribution of the initial state, we connect that with this initial growth. I never thought about connecting that with Lieb-Robson bound. And that would be a nice thing. Okay, because that, the width of the energy distribution is going to tell us, I have my initial state, is the first big spread is going to go, the width is going to determine, it goes. And then it slows down and other feature shows up. But that initial behavior is really the energies that, the components of the eigenstates are really contributing to that distribution. So maybe you can
because I'm thinking that the saturation that you are seeing looks like the behavior of the Lieb-Robson bound for the velocity. I mean, the Lieb-Robson velocity. I don't know if it's related actually, but it should be, because this depends on the correlations and the interactions between the systems. No? I mean, the speed of propagation.
Okay, now I don't know, but look, because the Lieb-Robson, now if I flip one magnetization, then you see the thing spreading. It's an easy thing to see in the chain. No? Now this is not really in the chain. What we are now looking is a spread in Hilbert space. No? So it's a many dimensional, but it would be a new kind of bound here. It would be the many
because the way
space bound.
Exactly, because the way I see Lieb-Robson bound is related with the, I mean, how fast those commutators that you showed before becomes non-zero.
Mm-hmm. Yeah,
I mean, because you showed an equation with a bunch of commutators.
Here, yeah.
And yeah, the commutators between different Hilbert different spins, which are different Hilbert spaces, they will become non-zero faster and faster. I mean, but I don't know. I can be wrong.
Yeah, I never understood the difference between the Lieb-Robson, the information that the OTOC gives you, that the Lieb-Robson. I mean, what's the extra information that this OTOC gives you beyond the Lieb-Robson?
Beyond Lieb-Robson, oh yeah, that's a good point. Yeah.
No, yeah, you're right, Tiago. Is especially if we are thinking like this in the chain, we are just seeing this spread. Now, the other entropy that we are talking about, we are not seeing this spread in the real space. We are seeing spread in the Hilbert space. If, like, try to make a drawing of that. I have one many body initial configuration, and we are going to go in a huge amount. It's not just two sides. No? It's like a tree decaying in all. I think that entropy is a little different from that.
Yeah, I see your point. You are spreading you spread information in different spaces.
Hilbert space, yeah.
Here yeah, in different. But maybe there is a connection. But anyway, thanks. Thank you very much. Oh, I put the link to the paper in the chat.
One second, let me.
I think, I mean, this is kind of related to the question I do, because like going back now to the last work you have, when you have this whole, no, I mean, actually when you look at these observables, I mean, any quantity you try to look at, I think there are many time scales, no, that you can have this, no, I mean, and there is actually an interesting paper when they get a spin model and they make some perturbation, and then they try to look at this, like you're going to have this diffusion scale, then you're going to have single particle dephasing, and then you're going to have multi-particle dephasing. So I think you really have this
different time scales.
Yeah. And also it would be nice to correlate, because there are also this, you have this picture of the excitation, you know? I mean, the quasi-particles spreading in your spin chain. So I think it would be nice to try to have a connected picture of all these things. I mean, how is this the time scale for your quasi-particles to spread, how is this related with the dephasing picture in the Hilbert space, because you have also this dephasing in the for the quasi-particles, no, because they come back and they don't interfere anymore. So I think this is kind of related, no, with the question.
In many body localization, there was a lot of this discussion, because if you, like in studies of localization, if you have a single particle, fine, people define the tau is time, which is the time for the particle to diffuse in the sample, and that's it. Now, when you have many interacting particles, what is tau is time? And we were talking about tau is time again, spread in this many body Hilbert space, but there is a discussion. Is it this diffusion in real space, or is it Hilbert space? Many body systems is a different story.
Yeah. And also, I mean, have you think, because there are also, I mean, so at the end you show that this correlation, this gap in the correlation hole, it's gonna, I mean, for large systems, it's not gonna be relevant anymore. No, it seems it's gonna.
For those quantities, for this survival probability is always there. It doesn't go away.
Oh, okay.
It's really, and even for random matrices, then we have analytical result. It's really robust. For other quantities, it shrinks. Yes.
Because I mean, always have look at the I mean, expectation value of local observables, and I never really look at this correlation role. And then I also was looking at this first decay. I was already calling it the equilibration time. No, even though I know there are many, and so, but I mean. There's also another question that I think we should be careful is which is the scale of the fluctuations that we're gonna call equilibration, no? Because there are many scales here that you should be.
Okay, but talking about everything that you're saying, even if you look at the survival probability, if Pedro picks one initial state, one realization, you're not going to see this. You're going to see noise here, and he will say, it's already saturated. Because it will be just fluctuations around this infinite time average. How do you see that? You have to do averages. These are small system sizes, so you have to do averages over disorder realizations, averages over initial states. Even this power law behavior, if you pick just one, you're not going to see. The only person who I saw, or work where I saw picking this power law behavior is a work by Mari Carmen Banyuls, because then she does DMRG, enormous system size, 50, 60, then she picked this power law behavior. Now, for the correlation hole, forget it. Even if you had a quantum computer, you wouldn't see that, because in this region, there is this property called self-averaging. So it's not self-averaging. You need to do averages, otherwise you do not see it. Yeah. So this is one. But then you had another question. I don't remember now what I was going to say. But yeah, but anyway, averages.
Okay, so you just see the correlation hole when you make averages over many realizations. Okay.
Then you will see it very clean. Now there are systems where you don't have disorder. So the way to see it is to do a time average. So you clean those fluctuations by doing a running, a running average is called. Then you can see it. And the size of the fluctuations that you're saying, well, we studied it after this region, after the whole, then once you passed correlations, then you can study the size of these fluctuations and then how it depends on the system size. That we did for different initial states, different models.
And usually it's exponentially small, I mean.
That is a good point. If it's chaotic system, middle of the spectrum, again, it decreases exponentially system size. If you go to edges of the spectrum, things become more difficult. The model where it doesn't decrease exponentially system size, XX, non-interacting system, then it's square root of the system size. It's much lower. But you can explore initial states, also models for the study of these fluctuations.
I mean, I also have a general comment, because I haven't been talking about this and nobody really seems to care much, because I think, I mean, in quantum mechanics, you always are expecting this exponential decay of the fluctuations of everything. But I mean, if you want to reproduce macroscopic thermodynamics, you don't need the exponential decay of the fluctuations. No, you just need a 1 over square root of n. This would be enough to get macroscopic thermodynamics or classical statistical physics. No, I mean,
yeah, well, that it would be small enough for large systems, that is true.
yeah.
But thermodynamics here, okay, because what I've been trying to be careful is one thing I called was equilibration. I reached that point where I just, the other thing is, okay, now that I reached this point, compare with a thermodynamic ensemble and so on. Yeah, but you're right. There are studies where people say, look, if I pick a regular system and depending on the quantity that I study, I see thermalization, even if the system is regular, but it's some special kinds of observables. If you want, I can send you a paper about that.
Yeah, I mean,
I'm just avoiding the polemic. I was saying, okay, equilibrated, that's it. Now, thermalization is a different question.
Yeah. I mean, I also more interested in the equilibration stuff than if it's going to thermalize or not. But I mean, I think that for you, your equilibrium state is always having fluctuations, no? Because we always talking about probabilistic equilibration. My point is that even if it's not a thermal state, it is still the fluctuations. They don't need to be.
Yeah. That's for sure. Even if it's GGE, whatever you're going to call, we do see this exponential decay with system size for these fluctuations. Yes.
But this one you have chaos. No, my point is maybe that, I mean, quantum mechanics allows
without chaos, I also saw this exponential decay. XXZ model, exponential decay. What matters there is a whole bunch of phases that makes it decay exponentially. It's not, yeah.
My point would be that even if you don't find exponential decay of the fluctuations, you're still good.
Okay, yes.
You still tell that this is equilibration somehow, I think.
Yeah, I agree with you. So we see exponential decay for some integrable models that have interaction, then it's really exponential. The other ones that are non-interacting XX, then it's square root of system size.
Okay, so Lea, do you have extra time or do you have some arrangement now? Because
I have a meeting, but I still have some time. Yeah, we can still talk a little more.
Okay. So for those who want to talk a little bit more.
This is still being recorded at YouTube?
Yes, it's being recorded. Yeah.
All the discussions, yeah.
Yeah, it's going to take some time to render all of these. But
well, I think you can end. I think you can end officially. I mean, and end the transmission for YouTube. Right?
Yes. Okay. So let me stop live